Hello to everybody. Here I am again, Gilberto Thomas, to present you these lectures about some extra tools and the features that CompuCell3D offers to you. At this lecture, we are going to see how to implement and visualize fields, vector fields and scalar fields in your simulation. And we are going to learn how to use the AdhesionFlex plugin. As a bonus, I may say, we are going to learn how to make movies and how to store output data from your simulation in your hard disk. Okay? Remember, this workshop is being live streamed on YouTube and recorded to be distributed later. Let's go. Here's the topics of the lectures. I will divide the lecture into two parts. The first one is the extra field talks. We are going to go over a brief review and an introduction about what is a field and the types that they can present in nature, how to represent those fields, and how to implement them in CC3D through three exercises, very simple. The second part is the AdhesionFlex plugin. We are going to see the introduction about cell adhesion molecules, and that will make clear why do we need an AdhesionFlex plugin. And also we are going to show this application through an exercise about cell sorting. We are going to reproduce the cell sorting now with this AdhesionFlex plugin. And from that exercise, we are going to learn how to make movies and how to save data from the simulation on your hard drive. Let's start by introducing some the concepts about field. What is a field in a physical, from a physical point of view? Okay. Okay, field it's a concept used to describe a region of the space which presents an alteration or a deformation of the space promoted by the quantity which is present in that space. Okay, we can see here three examples of a field. Gravity, magnetism, and heat. You can see this, both of these gravity and magnetism are vector fields that produce force over the pendulum here and over the magnet there. And here you can see nothing, but if you are close to the candle, you feel the heat around the candle. Okay, so from these examples, we can identify, I already told about, but two kinds of fields. One is the scalar one. The scalar field is a field that attributes to each point of the space where it is present a single number, which can be positive or negative. But for example, you see the sun at the left panel, and you see the temperature graph on the right panel. See, the colors there represents the temperature of each region. You have a scale at the bottom left, the map scale, when the temperatures are shown. So we only need a number to understand that one region is hotter than another. Nothing else than that. This is a concept of the idea for a scalar field. Only a number is enough to describe the physical quantity we are trying to study. In this case, temperature. Okay? The next one, it's a vector field. Differently, it is this field. Each point of the space where it is present, the quantity physical we are trying to describe, um, needs a vector to be assigned to the space, at each point of the space. Okay? For example, here, the gravitational field, we have, what is the quantity here? The quantity is the mass, Earth. This mass produces around it a gravity field, which is in a good approximation very near to the Earth by errors, the vectors pointed towards to the Earth. When you see that, you know that some object is put in this field, he will move towards the ground. In general, the zoom view from the Earth will show that the field, the gravity field, is like this right figure here. The field, the lines, the vector are radials to the Earth. Okay, so this is the basic difference. The scalar field only needs a number. The vector field needs a vector to describe the space. Okay, but even among these vector fields, I can give another example, which is the velocity field. The velocity field, I can play the movies here that you can understand here. Here are the clouds moving with some speed, velocity. And here is the representation of such clouds in motion. See, we have some small arrows here representing the direction of the wind. So while the gravitational field encodes how the space is influenced by the mass, by describing, for example, the acceleration, the gravity acceleration at each point around the mass, a velocity field captures the actual motion of the constituents inside that space. Then we can represent, for example, the rate and direction of the flow at very unique location. It's a motion, a vector in motion, if you want to say that. Yeah? This is what I just said. So one describe how the physical quantity modified the space. The velocity describe how the participants of the systems move in that space. Okay, how do they flow in this space? Okay, why I talked about the velocity field? Because another examples here, just to be complete. Here we have, I don't know why this time YouTube put some advertise here. Let's play everyone to see. I hope nothing weird appears. See, here we have a flock of birds flying. Here a flock of sheep moving in the country. And the last one, it's a flow of a fluid inside a tube. Here's the fluid, and here comes the field velocity. The field is representing the velocity of the particles of the fluid inside of the field, of the tube. See that the particles that are near the walls have slower speed than the ones in the center of the tube because of the the friction between the liquid and the walls of the tube. Okay, so this parabolic shape that you saw, it's a description of the uh, velocity field inside the pipe. Yeah? But there is another reason, another examples we can see here, which applies more to our scope in this course. This here we have cells in a tissue moving around, and here we have cells also moving, but in a kind of more oriented motion, like in a wound healing process. Okay, so this is why we are going to introduce these extra fields to help you to to visualize, for example, the components that constitute the cells that you have in your simulation, if that's the case, or if you have some extra quantity, like pressure, for example, you can build a pressure field for a field describing the nutrients on your environment, in your ECM, something like that. Everything you can. This Scalar, that is Scalar, is also uh, good for a good visualization field. Let's see then uh, how do we can use these fields for describing cell, in particular the vector field for cell movements. Okay, so we know that fields will help you to visualize the evolution of the individual system, but there is a problem. When you we use the wizard, okay, the extra fields aren't there. So here I put for completeness the manual web page for the extra fields in the CompuCell website. You can go there also if you want to a more detailed description. Uh, and talking about the wizard, the extra fields aren't here. So how to introduce them? Well, good for us. We can introduce them by hand inside to edit, going to CC3D Python drop-down menu. There is a line there. It presents you the extra fields, another sub-menu here with many possibilities for scalar fields and vector fields. Okay, uh, let's go there um, and see the levels here. Vamos try to explain what are cell level and pixel level. Cell level means that you are describing the cell as a whole by its center of mass. You use the center of mass steppable, and you have the position of center of mass for each cell during a simulation, and you can use it to put or take that center of mass as the point where you are going to measure the scalar field. You can use also the pixel level. I mean, you are going to describe the cell through every pixel of the cell. For example, if a cell is uh, extended enough to occupy some region of the environment that has different concentrations of nutrients, for example, the cell will be over a gradient of nutrients. So you describe this as a cell level, not in a center of mass level. Yeah? This is the same for scalar fields and vector fields. Both can be described at cell and at pixel level. Another thing you can see here is that there are two steps, two stages of implementing the fields. You have to make a declaration at the init function here, for example, to create the fields. And after that, you have to declare it in the step function to update the field, to manage the field, to alter the field, anything you want. Okay, so first in the init and then in the step. Okay, let's implement these extra fields through an exercise. Yeah? Okay, let's start with the scalar field. You can, we could start from the scratch, but it's more interesting to start with a built exercise that contains a, a, a field. Mm, we didn't mention field at that time, but now we can describe it as a field. The exercise about cell pressure, the exercise 2333, which we have in the student's material. Okay, the contact inhibits growth. Remember this exercise? We implemented it saying that after the growth is controlled by the pressure that the cells are underneath. So we have this function here, which has a preferential value. Any times that the cell pressure departs from this preferential value, the cell stops to grow, and everything in the simulation, remember, goes to a constant value. The target volume stops to grow, and the average pressure reaches a plateau here. Okay? Okay. Go in there. So you can use that. I'm comment the exercise here. Okay? You can load that project again, the 2333, and save it with another name, for example. Okay, save it E831, which is the number of the exercise. Of course, you can download again the exercise 831.zip from the demo codes in the student material, and then you can follow the lectures, I think, more easily. Okay, let's do that. I think it's more safer. I will wait for 1-2 minutes till you download that E831 code and open it into Edit. Let's go to the coding part. Okay. Uh, I will follow the steps to include the steppable, but you can look at the code you have to see what is inside the code. Okay, so remember, as I think it was Julio or Pedro that teach you how to add a new steppable in the simulation. You have to go to the steppable file, and inside the CC3D Python drop-down menu, you go to the option Add Steppable. In this option, when this option opens, is a new window open to configure the new steppable. Give it a name, for example, extra field visual, something like that. I don't know. Choose what you want, and say that is steppable for a scalar cell level field. Here, you can mark this box here. Click OK, and these lines here will appear in the main Python file. See, from the Steppable, oh, here I had the old name because I was working with the cell pressure file. So I have here the old name, okay? So this line will appear here. Import the new Steppable that you just created. This is automatically done in your main file. So now the Steppable file gets this default lines included. See, the at the in each part you create the field. Self-created. Let's take a look here. I think it's okay. Self-created scalar field cell level dot pi underscore pi, and with a default green words that is the name you have to give your file, your field, sorry. Yeah? The second line is, it's that usually line that any Steppable shows you by default, which is a loop to print the cell volume and cell type. Yeah? Okay, but now you have to put something else. Again, now, as I said before, you have to go to the step function and and to include the lines that we will manage the fields. Okay, so the first line here now you use that. You create the function because those lines are there already. So you have to change the name. So go to the init function here and change the name. Let's see how it goes. It's here. I'm creating for this example two fields. Remember the example, the cell inhibit growth, we have the graph for the average volume target volume and pressure. I'm going to see both fields. So I create both fields here. I duplicated that line that the wizard has included and gave it then two different names, pressure and volume. And I identified each creation here by field underscore P, field underscore V for pressure and volume. I have to use that to reference later both fields. I cannot use self-scalar fields for both because it's going to be confused. So I separated them. In these lines here, the next line, I will, in the step function, would create some placeholder for the values of the fields. Because when you create here, they don't have any information but their names. Now I have to fill the field with values. So we have to create the placeholders like this, put it to 0, as we always do when you declare a new variable, we put it to 0 to start. So I create the field and say that is empty. I created the volume field and it is empty. And then in this next loop here, I fill the fields. Remember that in this simulation, pressure was entry in the cell dictionary. We did that before. We don't. I didn't mention that because it's inside the steppable, the growth steppable uh, that we have built in the simulation E23 something. Huh? So I am filling the field pressure with the content of the dictionary of each cell, and the volume with the volume filled with the volume of each cell. Okay? Those, remember, are the variables that we are going to plot in the simulation. When you put the simulation to run for the first time, probably the field windows will not be shown. How do you show them? You go to this window tab here in the player, okay? And you see here the list of the windows that CompuCell has created for you. So if you want to see these windows, you click in each one of those extra 4 and 5, and these extra windows will appear in your simulation here. Then you can run the simulation. Does everybody got there? This is what you will see on your simulation. The cluster of cells growing here in the usual cell window, the graphics zero windows. The previous graphs for averages, cell targeted and cell pressure, and the corresponding fields. Look, the color here stands for the color bar here stands for the volumes of each cell and for the pressures of each cell inside the cluster. Yeah. In particular, here we have only one cell which has a very high pressure with 874 units here. And here in the volume, we have many cells with volume about 50 pixels, for example. Good. It's working. Okay, this is a very, very useful tool to, for example, if you had some chemical field in the extracellular matrix, you could map this nutrient field, this chemical field, in a window like that to see where the nutrients are more scarce or where are plenty of nutrients. Okay, it's a very useful tool for scalar fields, of course. Okay, let's go. And now the next is using the vector field. We are going to use Julius' exercise. I don't remember when I was writing the lecture yesterday if this number is correct one. Julio Beaumont built a simulation where he has a bunch of mitotic cells wandering around in the grid. Okay, we are going to use this exercise to attribute to each cell a vector, which will describe the velocity of each cell. Okay, again, this is in the exercise E832 in the student's materials. Okay. Let's analyze this simulation, the 832. download it from the 822 from the demo materials and open it to edit and let's look at it. Okay. Yes. Yes, Anastasia is the one you have to. Well, I don't know. I don't know if Julio has used the periodic boundary conditions. I don't remember that. But for sure, if the code has boundary conditions, periodic boundary conditions, you will certainly have the correction when the cell cross the border. Otherwise, it doesn't work. Okay. Okay, let's look at the code. We have two initial modifications here that will change the cell lambda volume to 4 from the old version, from Julius' version. And we have an extra modification here that we are going to limit the number of the cells in the grid to be 15 or 16. This is not to have room for the cells wandering around the grid. Otherwise, it will continue to split, to split, to split. So we are going to have the space full. Okay. The next is to again insert. You have this already. Okay. I'm just following the steps if you would build from the scratch. To add a new steppable from the Python menu, and now call again the extra visual steppable, but here in the choose of what kind of field you have to choose the vector cell level option, not the scalar as we did in the pressure example. Yeah? My error goes in the wrong slide. Now is here is the correction. The correction. Okay. See, um, if you have, I, we have to describe the speed, the velocity. Again, we have to calculate the velocity components as the variation of displacement over time. Okay, so we proceed line exactly as we did before in another simulation. Here is the time interval between measurements. Here is the placeholder for the vector fields, as we did in the pressure. Okay, and here is the calculation of the speed, the velocity components, the correction for the periodic boundary conditions here, the calculation of the speed, and we are going to put in the field velocity here. Remember, we created this velocity field, the vector field, and name it velocity here. And here, I put that velocity field in the placeholder called field. So field is an array where each element has three components. The vector components of the speed, the velocity. Since we are dealing only with 2D, 2D simulation, field cell here in the line 110 is filled with the x component of the velocity, of the cell velocity, y component of the cell velocity, and 0 because we don't have any motion in the z-axis. And then we store the actual position of the center of mass to be used in the next time we calculate the speed in the cell dictionaries. Okay, now it's this is I just explained everything here, but it's okay. If you there placeholder the algorithm for the cell speed calculation and put the components here to update this dictionary of the cell. I talk much more than I click the mouse. Okay, so then we can go and play. This is what we see. See, does everybody got this? Okay, in the right window, you have the regular cells wandering about around the grid. In the left window, you have the velocity fields, this, where each cell is described by a small triangle or a cone, if it were in 3D here, uh, which has a oriented direction. For example, this yellow one is pointed in that direction. The blue one is to the right, or the light blue here up, and they may have different size. I mean, the length of the arrows can be adjusted to really gives you the idea of how big is the speed of each cell. No, the color is amplitude, yes. The direction is only where the thinner part of the arrow points to. If you put the simulation to run, you see when the cell changes direction in the windows, in the cell windows, the corresponding arrow will change direction to follow the direction of the cell. In this bottom of the graphics, the velocity graphics, you can see the interval of the cell speeds. Okay, let's move on. Okay, guys, did you manage that? Did you have this image in your player? Okay. Now, let's do, this exercise is very, very beautiful. It's a toy model. I didn't present it in last forces and external potential because remember that slot was divided by me and by Michael. And I will show here um, the simulation where I have, this is the exercise at that lecture, a simulation where I have at left, it's a channel here. There is a constriction in the middle of the channel where the cells, the layer of the cells are being created at the left end of the channel, moves towards the right, in the right direction, and they should cross the constriction. And after crossing the constriction, they find a obstacle here. And then they disappear at the left end as if they were there a sink. Okay? So the cells move by external potential, cross the constriction, uh, find an obstacle, and leave the channel. Okay, this is the 833 E833 example in the demo materials. Okay? In this example, you can download it, please. I'm not going to, to save time. Let's analyze what happens. You can follow the lectures after if you want to. The steps are the same as we created the scalar field and the vector field. The thing is that in this example here, I'm going to create two fields, one of each type. One to describe the pressure that the cells are inside the channel, and the other, a vector field to describe the velocity of the cells inside the channel. Both fields. We are going to see it then in two different windows briefly. Okay? So the way to introduce the fields are the same as before. Go to the Python drop-down menu, insert the fields. For the vector field, you have to create again the dictionaries to calculate the velocities components. You have to, here you have uh, a step which is very interesting because remember, I told you at the beginning that the cells are being created at the left side of the channel, as it's a source of cells. So each time that a cell is created there, I have to to create also all the attributes that should have, that the new cell should have. For example, here I am not creating one. New cell, self-cell field. This creates a cell in the XY grid. Okay. Give to this cell a target value, a lambda value, and the lambda vec, the external component of the external field component of the force in the X direction. And I create to this new cell new dictionaries for it. You have to do that. Well, because a new cell has to be implemented completely with all the attributes that that kind of cell should have. Target, lambda, and any other behavior, like how to respond to the external force, the external potential. Okay, this is very important in this example. If you are creating cells, remember the mitotic Steppable does it for you for free. When you said self-clone cell in in the mitosis Steppable, it is doing exactly that. Now we have to do it by hand here. Okay. So here is the fields you have in the simulation file, the steppable one, the correction for the algorithms, everything. This is what I had saw in the previous exercise. Two placeholders, scalar and vector algorithm, placeholders for the fields, update to the dictionary entries. Now run the simulation. Please do it. and let me know what you have. Do you have these, guys? Oh, Anastasia, okay. See, the cells start by flowing from the left corner or left end of the pipe, move towards the external potential to the right, cross the constriction. See that in constriction there is a kind of continuity equation being showed here. See, the inside the constriction, the cells run faster. The colors are going to the red. Yeah. See, there is something here that I should mention in the pressure window. This is what I'm about to say, Anastasia. The red color in the medium says that the medium, look at the color bar here. The medium has pressure 0. No, remember, we have negative pressures here. So the 0 is about here. It's barely become orange, something like that in the scale. So when there is no pressure on the middle at all. But since the color starts from -20 here, the CompuCell puts some color to it, which is the color 0. Yes, it's the trick. Okay, I think it's a very nice toy example, toy model to show how to use both both fields at the same time. Yeah? At the same simulation, sure. Yes, it would be nice, yeah, James. It would be nice to be able to set a color, but I didn't. I don't know if that's possible for now. We have to request that improvement. Okay, let's move. Now let's go to the uh, new plugin. The second part is the AdhesionFlex plugin. Let's go a little bit uh, faster because time is running. So I will present a brief introduction about cell molecules, the types that we can find in nature, and finally the plugin through an exercise. And I forgot to change these numbers here. Sorry, people. These numbers here should be 8.3.4, 8.1, and so forth. I will correct later, and I will upload a corrected version at the slide materials on the website. Okay, let's go. Okay, when you talk about cell adhesion, it's a generalization that hides a lot of complicated mechanisms between cells, among cells and between cells and the environment, the extracellular or substrate that the cells are moving in or moving on to. So this is basically the types of the connection the cells have between cells and cell here, and cell and substrate, extracellular matrix here. Most of them are transmembranic connections. See, this line is entering into the cells, connected to the external world to to the internal body of the cell, inside the cytoplasm. Okay, so we have, for example, here these tight junctions, which are only at the surface, at the membrane of the cell. We have these junctions, adherent junctions, desmosomes, gap junctions, and so forth. A lot of things. Okay, I am a physicist. I'm going to skip these more detailed biological names here. Okay, then each one of these kind of connection between the cells and the cells in medium uh, are mediated by cell adhesion molecules, what we will abbreviate for CHEMs. Huh? They have lots of families for that. See? 4 families with lots of subdivisions of each family: integrins, immunoglobulin, selectins, cadherins, and inside each family is a bunch of them. Those are the type of connections between them. And one of those those, for example, cadherin is the most common interaction between cells, cell-cell interactions. They interact through these calcium-dependent connections like E cadherin, P cadherin, N cadherin, and so on, lots of them. Integrins, by their sides, are between the cell and the extracellular matrix. Sometimes some of them may interact between cells, but most of the members of the family act in between the cell to the ECM where the cell is. And then we have another types of families here, like the selectins that help the cells from the immune system to crawl through the blood vessels walls, and the immune cells and the endothelial cells for the other family here. Okay, there are complicated mechanisms, many complicated mechanisms. So the fact is, as we saw in the previous slide, a cell can adhere with through many different cell adhesion molecules, not only one. So the connection can be in a many different ways. Now, when we use the contact plugin, remember, here is the web page for the help of the contact plugin. This plugin doesn't make any difference about what kind of molecule we are dealing in our simulation. You just say that the cells have a contact energy expressed by the J valued among 2 pairs of cells. But now this new plugin, the AdhesionFlex, allows you to specify the type of the molecules the cells have, and better than that, can specify the density of each kind of molecule over the membrane. I'm saying that a cell can have a molecule 1, a molecule 2, but molecule 1 has much more receptors in the surface than the molecule 2. Okay, so we are going to introduce this new plugin, but before that, let's have a closer look at it. Okay, remember the contact energy, the energies are specified by the J's. Now there is a certain problem because if you have too many cells, the number of J's increases as n squared, where n is the number of kinds of cells, types of cells. If you have 10 types of cells, you have to define 100 J's for the matrix between the cells. Okay? This is turns your calculation very much more complicated and slow it down. Another thing, it's much more interesting that if you are going to explain adhesion, you may study, for example, the behavior of each kind of adhesion molecule the cell has. If the cells are, if you are trying to describe cell-cell interaction or cell medium or ECM interaction, you want to describe them differently from each other. The energies are different, much different, okay? And more than that, if you you are using the contact energy, uh, the concentration is the same for any kind of type of interaction you have. Okay, so the contact energy actually depends on many things. So let's have a look at it. This is the expression that the energy term that the plugin uh, that calculates inside CompuCell. But remember, we are going to implement this part inside the head frame here. Okay, so we are replacing the J by this sum. And this sum allows you to identify the concentrations of the catenaries, the concentration of molecules M and N at the cell I and the cell J. And they interact through a function, a bind formula that will be defined by you. You say, I want to the interaction be this way. Then you have the permission to do that, to define how is the interaction between molecule A and M and molecule N in different cells. Okay? And the KMN is the affinity between those molecules. They could be very fond of each other or they can hate each other. So this is what you have to define now in this new plugin. Okay, but there is another question here. Why you have this? Remember, the contact energy doesn't have this negative sign in front of it. Am I saying that I'm replacing the J for this expression here? So why there is this negative sign? Let's understand. Remember, the contact energy was this expression. We have this J here. This is this now. Okay? So it's positive. Oh, it may be in general is positive. And the lower value, the stronger the adhesion. Okay, for example, if J is 1, the cells adhere more than if J is 5. Okay? Now we are replacing by uh, uh, this expression in the red square. So F is the formula that interacts molecule M with molecule N. The default formula in the plugin is this one. The CompuCell takes the minimum concentration between the two molecules to be used as the binding between the two cells. Okay. For example, if molecule one has, for example, two as a concentration, and molecule N has 3 concentration, well, you can connect only 2 receptors. So the formula chooses the minimum for these numbers. Okay. So when this formula is used, it produces a positive number because concentrations are positive numbers. Okay. So this represented the degree of binding between the two molecules here. However, if you are using a positive number increases energy. So we have to use this minus sign here to say that we are changing for uh, use negative here because CompuCell internally does that. CompuCell, when you use the J's, automatically, internally, the CompuCell internally puts this value here, minus, in front of binding formula by binding parameter. Binding parameter is the K. Okay? Binding formula is this F here. So this is and when it does that, we have consistency with the dynamics that we need. I say high molecular match implies in high binding, which implies in negative adhesion energy, which is more favorable to the dynamics, and then the cells stick to the each other. So there is no secret about this negative signal there. Okay, I hope you got that. Yes, James. There is as I said before, we can choose another function for this form. Like you said in the chat, the product at concentrations would be more reasonable, or anything else. Okay, moving on. So here's the plugin. Again, we have this in the website, in the demos codes. Let's consider now a very simple simulation where you includes uh, uh, 2 species of dark to two species of cells, dark and light, to sort them. That cells will be in a blob of a radius 20 with width 5 in a grid 100 by 100, and interactions we should interaction through two chems, chem1 and chem2. And the plugins we are going to include now is AdhesionFlex, VolumeFlex, SurfaceFlex, and center of mass, which is hidden behind the picture here. Yeah. So let's go. Here you can download it, but I will go through this image here. And when we got
Sorry,
to
there was a
this,
question about what is the number of the demo in the folder?
834. Sorry. 834. Oh. Okay. When you use the wizard by the way you have been using for 10 days, almost 10 days already, when you notice that I'm not choosing the contact, I'm replacing the contact plugin here for the AdhesionFlex here. Okay? And I am using this volume. I forgot to mark here the surface flex, and the center of mass is marked. But when you click next at this screen, a new window will open now. The window where you configure the AdhesionFlex plugin, or is the space where you input the adhesion molecules, as pretty much the same way you include the cells in the cell window types. Yeah. So you click here the number of the molecule and the function which this molecule will obey, the formula, and click Add. Put the second one, click it Add, and then finish the simulation. Okay? For here it's a kind of small, but I put it this way to see every part of the XML file. I cleaned it a little bit to get rid of the comments to fit in the screen. We have the pods part, the cell types, the volume plugin, the surface plugin, the center of mass plugin, and the AdhesionFlex plugin here. Here is the information about the exercise. Okay, let's see in more details, analyze in more details the AdhesionFlex part. Here it is. Now you can read better and you can follow the loaded exercise you have. So going part by parts, here are the definition of the molecules in the plugin, Chem1 and Chem2. Next, you have the densities. When you use the wizard, there will be default values here. But at this example, I am giving you the correct values for the simulation to work. Okay, so for example, cell dark has Chem1 with density 6.1, Chem2 with density 4.1. The light cells has molecule Chem1 density 2.1, and the density of Chem2 3.1. Okay, this is the M and N in that previous formula. Next, we have the formula and the binding parameters. The formula we have chosen in the last window of the wizard is minimum of molecule 1 and molecule 2 in the line here. And the variables I have chosen for the bindings, 0.5, 0.05, 0.25 for the interaction between Chem1, 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 Chem2, Chem2, Chem2. This is the matrix. I'm saying what are the affinities between each part of molecules. Okay. Now you can run the code. If you put it to run, you see very quickly that you have the sorting where the dark cells, the blue cells, go inside are engulfed by the yellow light cells. Hey guys, did you got this? This is easy. With the code red is much easier. Okay, I hope everybody has. Yeah, so I will finish this. So this small example shows you how to play with this molecule stuff. See, one thing I should mention in this, I will go back a few slides here. Should mention in this is that, see, since at this point here, please look at the slide, at the code. I have as default, since I include two kind of cell molecules, and we always have in the simulation the medium, okay? There are the next two lines here gives you the density of molecules Chem1 and Chem2 to the medium. But however, medium doesn't interact through caderins. Yeah, I'm using this example to show the interaction between cell and cell sort. So I don't have any interaction with the medium. So I comment this line. I got rid of the interaction between medium and the cells. There is no interaction between medium and the cell. And since I did not include the contact energy plugin, I really don't have interaction with the medium. Okay? So I comment those two lines here. If I had some, for example, we introduced a third molecule like an integrin, then I will have lines including the density of integrins for the medium, for example. And I have to include these interactions here in the adhesion interaction matrix for molecule integrin with Chem1, Chem2, or something like that. Okay. Actually, I would have to include the integrins for the cells as well. Okay, to interact with the medium, the cells would have also to have integrins are adhesion molecules together in here in its surface. Okay, now I can pass through. Okay, now an extra feature for CompuCell. How to make movies in CompuCell3D. Okay, I try to be quick in this way because I think you have seen this 2 or 3 times before, also very quickly. But let's see. To make a movie, you have to start the simulation not from inside the player, sorry, not from inside it to edit, but you have to start the player instead. Okay, so you open a player directly by clicking on the icon CC3 CompuCell 3D.bat on your desktop, and the player opens. You load the simulation, and be sure. No, first of that, click on that step button twice. This will make your simulation run one Monte Carlo step only. Okay. Now we will go to the tools tab. Before that, I didn't put this because I remembered after. You have to define where your simulation is, and I mean the place where you want to save the files, the images to make the movie. Okay. When you click the tools, you have in the configuration window, you have the setup. The setup tells you where are your projects. Sometimes when you are running a project and you stop to run that project to open another project, a different one, the player doesn't update that setup. So you have to make sure that you are working in the right folder. You have to update your setup by hand. So my new project is in this folder. Okay? I hope you get that. Okay, now once you are sure that your simulation is running in the right folder, you advance and click here in this small icon, which has a camera, and that click will prepare the player. How do we check the folder we are in? Okay, let me show something here. I will open here quickly a simulation here. For example, I have this one here, A34 loaded here. I go to Tools, Configuration. In the setup here, I can see that this simulation I am running here, E834 right. The setup is put in the E834 and not in the 834 right. So I have to correct this. Otherwise, anything that is going to be saved for the movies, it will be saved in this folder here, not in the 834 right folder. Understood that? Because otherwise you are going to be lost. You are running a simulation that you think that is in one place, it is going to be in another folder you don't know. Okay. Cancel, close it, and come back. Okay. Once you click here, CompuCell save is prepared to save images. Okay. So you have to continue the configuration and open again this new tools. The one I just opened inside the player to show the setup, and go to the screenshot in screenshots movies and configure the saving of images. So here I'm saving the image at each, I click out this square box here, at each Monte Carlo, 100 Monte Carlo step, I can refine or change the resolution of the image. And I can say, okay, when I do the movie, I want to write the Monte Carlo step on each frame of the movie. Okay? See, there is another blank square here, which says save movie automatically every time the simulation stops. what does that mean? That when your simulation finish by time, or when you click it to stop, CompuCell, the player will automatically make the move for you. Unfortunately, this is not working because I don't know. Okay, so, but we still are in game. Let's go on. I will tell you how to proceed. Okay? Okay. Inside that, oh, you have to run the simulation now. When you run the simulation, CompuCell creates inside your workspace that one that you have defined in the setup a folder which has inside a subfolder called cell fields 2D XY0, which with this name here, okay? And this subfolder will be the folder where the images will be stored. And there is another subfolder called screenshot data, which is not important for you. It's important for the player to read information about the images. This is a working directory for the player. Okay? And when you enter in that field, in that folder, sorry, you have the images there, like this. Okay? Please give it a try, see if you have this working this folder did not get generated for me. Or are you in the right folder, Anastasia? In setup? So once you, let's try to do the following. Once you click in the button, you don't have a folder called, let's see here. Let me show if I can. Uh, 83, no, 834. Just a second. See, every time the CompuCell run, it saves a folder like that, which has the timestamp for the simulation. August 6, 2025 at 13:19:42. I don't know why it's so wrong this time it's here. Oh, no, this is I created early today. Okay. Inside that folder, you have that cell field, blah, blah, blah. Do you have that? Let's see the image you sent. No, it's not creating. Ah, okay. Did you get it? What was wrong? Okay, you get it. Let me go on because time is running. Okay, so inside this second subfolder, you have the images. Ah, see, it was making my folder my CC3D folder, not the local folder. Yes, that's why I told you before. If you don't pay attention to the setup, you may never find your results. Usually, by default, when we install CC3D, CompuCell3D, it makes a default folder in the Windows users your name CC3D workspace. And if you not define a new folder to work, Everything is going to be there. Okay? So now you have the image inside the cell field folder. You see that the folder stores the images with timestamps for each image, 0, 500, 1,000, and so on. The Monte Carlo steps is in the name of the image file. Now let's make the movie. Remember, since that right move was not working, we have to do it by hand. So from inside the CompuCell player, I mean, you stop CompuCell player, the simulation, you stop the simulation because it's running for 100,000 Monte Carlo steps, you can stop it right now. So open the tools configuration, go to the screenshot movies tab like here, and go here, create movie now. Okay? From inside the player. Okay, don't close the player before do that. So once you click in this button, a second browser, file manager browser opens, and you have to select where is your files. Where are your files? So you choose that file, the time-stamped file with the images, and select folder. And the player will click the button, select the folder, and the player will make the move for you. Oh, somebody is in a Mac. Oh, which tick box was not being working, Clara? The make a movie, create a movie. Did you get it working, Clara? Okay, thanks. So when you finish this clicking, the CompuCell creates the movie and puts this message here, movie successfully made. Then the final step is to, before that, comment here. When it creates the movies will be inside another subfolder called movies inside your time-stamped main folder. These movies are here. When you open it, show the movie on file. The other button in the configurator, show the movie on file. You open that folder movies that shows you the built movie. Now you can click on it and play it. And see there is the timestamps here working with the simulation I did. Oops. Taylor has a bug for that. I don't know how to solve this. Does anyone knows? No? FF MPEG, that should be installed with a CompuCell installation. Yes, of course. You also, it's more, if you want to build the simulation later and this failed, try to, after that, to reinstall CompuCell or before reinstall, you close, start over the player, start the simulation again, do everything again, and try to make the movie again. If it fails, then maybe you have to reinstall CompuCell to have this. Not today, of course, but eventually. Otherwise, you never get this work. Moving on. Now the final task is how to save that data from your outputs, from your simulation, from inside the simulation. Suppose you want to keep track of a bunch of information that your simulation is calculating, like concentrations, volume, pressures, anything, okay? So you want to save it in your hard drive to analyze the data after. Okay, let's know how to do that. Let's use the previous exercise uh, to do that. There. So you have to make some, suppose for this simple exercise, you want to keep track for the properties of a given cell. Say the cell whose ID is the number 40. Okay, so at the start function, I define of the Steppable, I define a variable to say, okay, the cell I want to keep track is this cell ID number 40. Next, I define the output file and where it's going to be stored. Okay, CompuCell has intrinsically a variable called output dir. Output dir, he takes the CompuCell takes the value for this variable from the setup of your simulation. Okay, so this value will be what you have written in the setup of your simulation. I mean, where is your project? And where is the outputs of your project? You remember, you have two lines in that setup, project folder and output folder. Okay, so here is going to took that output value that you wrote there. Okay, so this is the folder for the output. Self, I called a new variable called dir, and put in that variable self output there, because could be anything. Okay, you can define, you can change the output dir, that's possible. You can look for how to change this output dir. Anyway, so the next thing is define the output. I mean, the output path is the total path for your output. I mean, the output folder plus the file name. The file name of the where your data will be stored. Okay? So I'm telling that here that the file name is a composition where I will write in the file name, in the name of the file, which cell ID I'm tracking. See here, in the green part, cell ID number, cell ID, which is 40. Another information, for example, is what size of grid size I'm dealing. My simulation is working. I'll put here self underscore grid size underscore plus self dim x, which is the x dimension of my grid. So the name of this file would be cell ID 40, grid size 100. This is the name. Why you do that? Well, because when you are playing with parameters, you have a bunch of simulations to replicate, to vary. You want to identify, looking at your files, which data you have used in that particular simulation. The best place is to have this is in the name of that output file. Okay? You can put as long as you want this thing here. You could put a cell ID, cell volume, target, anything, type, anything here. You can build a name with any information from your simulation here. Okay? And at the end of this file here, I add an extension like this one. Self data is the output, which is inside the blue frame here, plus cell data dot depth. This is creating the full name of the output file. Okay? Next, I created the data. I opened the data with the option write. Okay? So this line here creates the file for the data write access in this output in the dir folder you have defined here. The second line here, I'm creating this header for the file name, for the file. The first line of your output file is time, surface, cell surface, and cell volume. This is the sequence of the information I will store in that file. Give it to instruction to write this amount of information per line, and I close it by force. Remember to always open and close your file at the same time. I mean, after you open, write, and close. Okay, I will tell later a little bit more. So here, the next step is to fill the file. So at the step file, which can be as any time is interval you want, you write the data in that file. So here is the loop. For each Monte Carlo step, in this case, I do a loop in the cell, pick the cell ID number 40 that I have decided to follow, open the data, the file, open to add information here. Remember this particular instruction to open command, the Python open command here. This is to add information to the file. You have to put that, otherwise it will write the new information over the previous one. And I define in the next line the format for reading the data. It's a format real with 8 decimal cases, whatever. And the sequence of the information I have to store. MCS for time, cell surface for cell surface, cell volume for cell volume. And I close immediately the file. Why should I close it so fast? Because you don't want to lose information. If for any reason suppose you are storing continuously with the file open, okay? If your simulation crashes or stops by any reason, you lose everything because you lose all the data because the operational system doesn't dump the content of the buffer if you don't say it to do. And the way to say it to do that, to really write to disk, is to close the file. Then the system will write in the disk. Okay? You can follow this example in this demo code E835W for writing. What about a question? What about if you want to save an image plot? You can do that well, the images you saved as we did before. You can say to the player to save images at any Monte Carlo step. And from Python, you can save images from Python using the one instruction from inside, I think, the scientific plots. I'm quite sure that you can
No,
have
but
that.
the question is to save the screenshot from Python.
Well, if you have a graph, see, if you have
Not a
for
graph
the
of the
cell
cells
window,
of
I
the
don't
cell
know.
field.
The
The
cell
cell
field,
field or the chemical field.
I don't know. I don't think it can. In
It
that
should be
case,
possible. It should be possible, but I actually don't know how to do it.
I don't know either. It's a good question.
No, Matplotlib wouldn't help you because you have to render the boundaries of the cells. That's why it's a little complicated.
Yeah. Okay.
You could certainly save the values of the field, and if you don't care about drawing the boundaries of the cells, it's easy. The question is, how do you save the rendered images? And that I don't know.
Yeah, I don't
It's
know
too
either.
bad we didn't ask Maciek while he was here.
Oh, yeah.
It's certainly there in the C++ code, but I'm not sure how to do it. That's a great question.
So here is how the output data will appear at your uh, output. This is an old picture. I don't know if I have a new one. I don't think I have. Let's see. So, but anyway, the first part is the working folder, and from the first underscore to the end is the part where I wrote the identification for the simulation I just did. cell 40, cell ID number 40, grid size 100, cell data dot dot. And when you open it, you have this picture on your right side of the window, time, cell surf, and cell volume, and the formats with eight decimal cases after the comma. For each Monte Carlo step, you have for the cell 40 volume, surface, and volume. Then, oops, sorry, you have everything stores if you need it. Okay, that's it. I think with this example of keep how to keep your data saved, I can end my lecture today. But before I go, I have one comment to do just for for comment really. This is the summary what we have learned all this since we began on last Monday, past week. We have we have saw a lot of things, a lot of tools, a lot of philosophies, if you want, if you talk about how to modeling, that network modeling part from James, and how to make models as fundamentals of modeling, plugins like the volume is great, and examples, a bunch of things. I think this is going to be very useful for you to help with simulations, and we are very glad that you could help it.